Hello everyone and welcome. Today we are going to get into one of the most fundamental topics that powers our entire world, current electricity. So whether you're getting ready for an exam or you're just a little curious about what's actually going on inside all those wires around us, you are in the perfect place. We're going to break it all down step by step and make it all make sense.
I mean, have you ever really stopped to think about it? Every single day, we're flipping switches, charging our phones, using all these appliances without even a second thought. But behind all of that, there's this invisible, super powerful flow. So let's pull back the curtain and really get into what that flow is all about, starting with the absolute basics.
To understand how any of our gadgets work, we have to start with the three core ideas that everything else is built on: current, voltage, and resistance. I like to think of them as a set of dominoes. Once you get the first one, the rest just start to fall into place. So let's start with that very first domino, the current itself.
At its very heart, electricity is really just about movement, specifically the movement of these tiny charged particles called electrons. When these electrons start flowing through something like a copper wire, a conductor, we call that an electric current. And we measure this flow in a unit called the ampere, or just A for short. So what makes these charges move in the first place? Well, they don't just decide to go for a walk on their own. They need a push. In electronics, we call that push potential difference, but you and I know it by its much more common name, voltage. It's kind of like water pressure in a pipe. The more pressure you have, the stronger the flow of water. In a circuit, more voltage means a stronger flow of current. We measure this electrical pressure in volts.
Okay, so as this current is flowing along, it doesn't get a completely free ride. The material it's flowing through actually pushes back a little bit. It obstructs the flow. And this opposition is what we call resistance. Every single thing in a circuit has some resistance. We measure it in a unit called ohms, and we represent it with the Greek letter omega.
Okay, so we've got a flow, that's current, we've got a push, that's voltage, and we have an obstacle, which is resistance. But how do these three things actually relate to each other? Well, that's where one of the most important laws in all of physics comes into play: Ohm's law.
And there it is. This simple, really elegant formula, V equals I times R, is basically the heart of electronics. It perfectly shows how voltage, current, and resistance are all tied together mathematically. If you know any two of them, you can always figure out the third. This is the cornerstone for understanding any circuit.
Now, the formal way of saying it is that the current flowing through a conductor is directly proportional to the potential difference. But there's a really important catch: provided that the physical conditions and the temperature of the conductor remain constant.
And this is a super important point that a lot of people miss. Ohm's law isn't universal like gravity is. It's something we observe that holds true, but only under specific conditions. It really only works perfectly if the conductor's temperature doesn't change. Think about the tiny filament in an old light bulb. As it heats up to glow, its resistance actually goes up, and that simple V equals IR relationship gets a little bit trickier.
What's so great about this graph is that it gives us a visual proof of Ohm's law. For any material that follows the law, if you plot the voltage versus the current, you get a perfectly straight line. And this isn't just a neat visual, it's a diagnostic tool. If you tested a component and its graph was curved, you'd know right away that its resistance changes, and it's what we call a non-ohmic device. Plus, the steepness of this line, its slope, tells you the resistance at a glance. A steeper line means higher resistance.
All right, so with the core rule of Ohm's law under our belts, we can now move on from just talking about individual components to seeing how they work together when we start building actual circuits.
Fundamentally, there are really only two ways you can connect things: in series or in parallel. Think of series as a single-lane road. All the traffic, which is our current, has to follow the exact same path, so the current is the same everywhere. The total resistance is easy. You just add up all the individual roadblocks. Parallel, on the other hand, is like a road that splits into multiple lanes. The current divides up, taking different paths. But the voltage is the same for everyone. The formula for total resistance is a little more involved, because, well, there are more paths for the current to take.
And here is a perfect picture of a parallel circuit. You can see the total current leaves the battery, and then when it gets to that junction, it splits. Some of it goes through resistor R1, and the rest goes through R2. This is exactly how the wiring in our homes works. It's all in parallel. That way, every appliance, whether it's a lamp or your TV, gets the same full voltage from the outlet, and you can turn them on and off independently.
So let's talk about the power source for a second. We usually talk about a battery's voltage, but the full technical term for its total potential is electromotive force, or EMF. Now, this is a kind of old, misleading name. It's not a force at all. It's much better to think of it as the maximum possible voltage a battery can supply. It represents the total energy it gives to each little bit of charge to make one full lap through the entire circuit, and that includes the journey back through the battery itself.
This slide shows a really crucial real-world difference. EMF is the battery's ideal voltage. It's what you'd measure if the battery was just sitting there, not connected to anything. But the second you connect a light bulb and current starts to flow, the battery actually has to do work to push that current through its own internal chemistry. It has its own internal resistance, and that effort uses up a tiny bit of its own voltage. So the voltage that's left over for the actual circuit, which we call the terminal voltage, is always just a little bit less than the ideal EMF.
We've covered the flow, the push, the opposition, and the circuits. But, why do we even build circuits in the first place? To do work. And that brings us to our final big ideas: electrical energy and power.
Power is really all about how fast energy is being used. So electrical power is simply the rate at which electrical energy is turned into other forms, like light, heat, or sound, in a circuit. Its SI unit is the watt.
This makes the idea of wattage really simple to get your head around. When you see a light bulb that's rated at 100 watts, it literally means that for every single second it's turned on, it is eating up 100 joules of electrical energy and turning it into light and heat.
Now, while the official SI unit for energy is the joule, it's a really tiny unit. For practical things like your electricity bill, the company uses a much larger unit, the kilowatt hour. This is the one you actually see and pay for.
So how do these two units relate to each other? Well, 1 kilowatt hour, that unit on your bill, is equal to a whopping 3.6 million joules. This isn't just some random number. It's the total energy that a 1,000-watt appliance, like a small heater, would use if it was running for 1 full hour. This is a key conversion you will definitely want to remember.
So, let's just quickly recap that domino effect we followed. We start with the current, the flow. That current immediately runs into resistance. The relationship between them is perfectly described by Ohm's law. We then use that law to build and understand circuits. And the entire reason we build those circuits is to deliver power to do useful work. It's a perfect chain of logic, where each idea leads right to the next one.
And that brings us to one final thought. We've seen that resistance is useful, right? It's what makes a toaster work and a light bulb glow. But over hundreds of kilometers of power lines, that very same resistance causes energy to just be lost as heat. So here's the puzzle for you. How do power companies send huge amounts of electricity across the country without most of it just ending up warming the wires? The answer is hidden in the relationships we've just talked about, especially Ohm's law and the formulas for power. Something to think about. Thanks for joining this explainer.